We're going to look at three very important discrete probability distributions. They show up all the time in statistics, and those distributions are the uniform distribution, the Bernoulli distribution, and the binomial distribution. Let's start with the uniform distribution. So the word uniform means that everything is the same. So consider the following experiment. You're going to roll a die, and X is going to represent the number you roll. So X could be 1, 2, 3, 4, 5, or 6. And the chance that you roll a 1 is the same as the chance of you rolling a 2 or a 3, and so on. And so if we make a bar graph that shows all of the possible values for X, the range, along with the probabilities, since they all have the same probability, the bars are all the same height. And we call this the uniform distribution. Let's see some more examples of uniform distributions. So if you walk up to a random person on the street and you guess their birthday, without any other information, you're just guessing their birthday, the probability that you guess the right date is 1 out of 365. So if we make a bar graph with all the different dates, all of the bars would have the same height because they all have the same chance of being chosen or being that person's birthday. If you spin the spinner to the right, notice that all of the colors have the same chance of being selected. There's 5 colors, and the probability that you land on a yellow is 1 out of 5, and that's the same probability as landing on green. So as a bar graph, if we put the names of the colors on the x-axis, all of the bars would have the same height, so this is a uniform distribution. Consider the following experiment. You're going to randomly draw a number from 1 to 100 out of a hat. Now, depending on how I define x, can change the distribution. If I said, let x represent the number I draw out of the hat, then the range of x would be the numbers 1 through 100, and my bar graph would have a uniform distribution because all of the numbers have the same chance of being selected. However, here I'm saying x represents the number of 4s I draw. If I'm drawing one number out of a hat, I either draw a 4 or I do not draw a 4. So not drawing a 4 means x is equal to 0, and drawing a 4 means x is equal to 1. So those are the possible outcomes, just 0 and 1. Now when x is equal to 0, I do not draw a 4, and there's 99 numbers out of 100 that are not 4s. While my success, drawing a 4, that probability is 1 out of 100. X is 0 is thought of as a failure, and x is 1 is thought of as a success. My bar graph will only have 2 bars, and in this particular situation, the failure bar is much taller than the success bar. This is called a Bernoulli distribution. Bernoulli is the last name of a mathematician who contributed a lot to statistics, and they named this type of distribution after him. So here I'm summarizing Bernoulli distributions. So Bernoulli distributions are where you have a random variable x with only 2 options, 0 and 1. 0 is considered a failure, 1 is considered a success. The probability of success is some value. We call it p. In the last example, we saw that the probability of success was 1 over 100. That was p. And the probability of failure is always the complement of the event of a success. So it's 1 minus p. That is the probability of failure. In the last example, the failure rate was 99 out of 100. The expected value of a Bernoulli distribution is always equal to the probability of success. You can verify this by making a table, letting x be 0 and 1, and then the probability of failure, for example, in the last one was 99 out of 100. The probability of success was 1 out of 100. Find the expected value, and you'll see that you'll get 1 out of 100, which is the probability of success. Let's say you draw one card from a deck, and y represents the number of jacks you draw. What kind of distribution is this? Well, the range of y is 0 and 1. You either draw a jack or you don't. This is like success failure. The probability of drawing a jack is 4 out of 52. the probability of not drawing a jack is 48 out of 52. This is a Bernoulli distribution. The only difference between this one and the last one is the bars. The success bar is just a little bit taller in this case. One of the questions on the homework will be, here's a scenario, and I want you to tell me what type of distribution do I have? Here's some more examples of Bernoulli distributions. So if you flip a coin and you let X represent the number of heads, you just flip a coin once. This would be a Bernoulli distribution, and it's also uniform. So here's a situation where you could say this is uniform because the bars have the same height, but it's also Bernoulli. If you roll a die and X counts the number of heads, this is Bernoulli. And let's say you buy a coat from Amazon. There's a chance that you get a defective product, but there's a higher chance that you don't get a defective product. If X is receiving a non-defective product, X is equal to 1 means you received a non-defective product. That's more likely than receiving a defective product. So in a Bernoulli distribution, you always have two bars. X is 0 and one bar may be taller than the other. Let's say you play a game where you pay $1 to spin a wheel, numbered 1 through 10, and if it lands on 8, you get $5, and if it lands on any other number, you get $0. Let X represent the net change in your money after one round. Is this a Bernoulli distribution? Well, you do have two options. We've seen this example before. You have two options, and those two options is X is equal to -1 because you lose your dollar if you don't land on an 8, and X is equal to 4. That's if you land on an 8, your net change is 4. You made a profit of 4. Now, all it depends on how X is defined. Yes, you do have two options, but X is not equal to 0 and 1. Thus, it is not a Bernoulli distribution. In order for it to be Bernoulli, X has to be 0 and 1. Okay, we're going to move on and we're going to talk about the binomial distribution. The thing is, we need to understand some mathematics in order for us to really get what's happening with the binomial distribution. The first thing is we're going to talk about n factorial. N factorial is n with an exclamation mark behind it. And what that means is we're going to take whatever number n is and multiply all the numbers behind it until we get to 1. For example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So we take 6 and then we subtract 1. We get 5, subtract 1, 4, multiply all the way until we get to 1. So 100 factorial would be 100 times 99 times 98, and you continue until you get to 1. Here are two more examples. 2 factorial is just 2 times 1. 1 factorial is just 1. And we're going to define 0 factorial as 1. Then there's something called n choose k. N choose k is read as n choose k, and it looks like this parentheses with an n on top and a k on the bottom. And what it's really equal to is n factorial divided by k factorial, and then we take n and subtract k and factorialize that as well. So what I want to do is I want to show you how to do this by hand, and then we will see how to do it with Excel. And you can also use your calculator as long as it's a scientific calculator. There should be a button for you to find this. Sometimes there's a little C, NCK. It means the same thing. If you can find this button on your calculator, you're able to find all of the answers you'll see here. So what I'm trying to do is I'm going to show you how to do it by hand, just so you understand what's going on. But we will use calculators to actually calculate this value here. So let's work with 5 choose 2. 5 choose 2, we're just following the formula. On the top we put 5 with a factorial, so exclamation mark. On the bottom it says k factorial, so the number on the bottom, 2 factorial, and then we subtract the two numbers, 5 minus 2, and we get 3 factorial. Now, 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. And 3 factorial is 3 times 2 times 1. So I'm just writing out all of the numbers. Then I'm canceling what we have in common. If you have something in the top and the bottom, you can cancel them out. And we get 20 over 2, which is equal to 10. So 5 choose 2 is equal to 10. If you have a scientific calculator, you need to find this button in your calculator. If you don't know where the button is, you can just Google N choose K and your calculator, and you should be able to find it, like a YouTube video or some manual that tells you where this button is. But we can do this in Excel, and the Excel formula is equals to COMBIN, in parentheses, you put N, comma, your K. So let's take a minute and see if we can actually put this into Microsoft Excel or Google Sheets. Okay, so you should be able to see my spreadsheet, and at the top, I've just written that formula, combination NK. So what I'm going to do to double check, now we were trying to find 5 choose 2. So in some random cell, I'm going to type equals COMBIN. And if I want to do 5 choose 2, you can see already it's telling me what is n. N is equal to 5. Then I'm going to put comma, and then I'm going to put 2 parentheses and hit enter, and I get 10. Let's try another one. Let's do 6 choose 4 because that's the next option we'll see in the PowerPoint presentation. So we're going to do equals COMBIN parentheses 6 comma 4. That's 6 choose 4, and we get 15. So 5 choose 2 is equal to 10. What does this number actually represent? What is this 10? Why do we have this very complicated formula in order to get the number 10? So what I can think about is if I have 5 spots, so I'm going to put 5 little dashes to represent spots. And in those 5 spots, I want to put 2 checks and 3 X's. How many different ways can I move those checks around in those 5 spots? So for example, here I have my 5 spots and 2 checks, and I put the 2 checks in the front and the 3 X's in the back. If I move those checks around, like here, now I have 1 check in the very front, and then the second check is in the 3rd position. How many different ways can I move those checks around? So here's another example. I dropped the X's, but you can imagine there's 3 X's, and here are the 2 checks. And then here's another way to move those checks around that's different from the other 3. There's a total of 10 ways to move those checks around. These are all of the different ways to move those checks. And so what this formula is counting how many different ways we can move these checks around. So the checks are like successes, and then the other 3 are like failures. Now we found 6 choose 4 in the Excel spreadsheet. Here I'm going to work the problem out and show you that it is 15. So following the formula, and you can pause the video if you need to double check, but this is plugging everything into that formula. I get 6 factorial over 4 factorial times 2 factorial. Now I'm going to write out what 6 factorial, 4 factorial, and 2 factorial are. And then I'm going to mark out anything that I have in common in the numerator and the denominator. And so I get 30 over 2, which is 15. That is what I found earlier. So what does 6 choose 4 represent? If I have 6 spots and I want to put 4 of them as checks and 2 of them as X's, how many different ways can I move those 4 checks around? Well, it turns out there's 15 different ways. If you're curious, you can try that, see how many different ways you can move those checks around. You should get 15 different ways. 9, choose 1. Let's see if we can actually figure this one out in our heads. So remember that 9, choose 1 is like 9 spots, and I want to put one check in those 9 spots, and the rest are X's. So I could put the check in the first spot, and the rest are X's. That's one way. Or I could put the check in the second spot and put X's everywhere else. The check in the third spot, the fourth spot, all the way to the ninth spot. So how many different ways can I move that check around? Well, there's 9 ways. And you can use the formula to double check that. So this one you can figure out easily in your head. And also the last one. The last one is 1 because it would be 8 spots with no checks. If all of them are X's, then there's no way to move checks around. There's just one way to do 8 spots with all X's. Okay, now we're going to get into the binomial distribution. We're going to work through this slowly. I'm going to explain things as I go, and then in the future, you'll be able to see a problem, know that it's a binomial distribution, and just use the formula. So here we have a hat with the numbers 1 through 100 inside. You're going to draw exactly 3 numbers out of the hat, one at a time with replacement. So every time I draw a number, I put it back into the hat. We're going to let X represent the number of 74s we draw. This is different than in the past. In the past, we drew one number and it was Bernoulli. Here we're drawing 3 numbers with replacement. X represents the number of 74s I draw. What is the range of X? What are all the possible things X could be? Well, I could draw a 5, 5, and a 5, right? That could happen. And that would mean X is 0. I did not draw any 74s. Okay, so X could be 0. I could draw exactly 174. I could get the 74 on the first draw and then 75, 75. I could draw 2 74s. And the maximum number of 74s I could draw is 3. If every time I drew a 74, I'd have, because I'm only drawing 3 numbers, the maximum I can have is 3. So the range is 0 through 3. Don't forget that 0. That's a common mistake to forget the 0. Now let's try to find the probabilities of each one of these outcomes in the range. Let's start with the probability X is 0. This is actually nothing different, this particular probability. We have done this in the past. The probability X is 0 means that each time I drew a card out of the hat, it was not a 74, right? So there are 99 other numbers because the cards, I'm thinking of cards in a hat, all have the numbers 1 through 100 inside. There's 99 other numbers. So the probability that X is 0 means I don't have any 74s. The first one was not a 74. And notice that these are independent events, so all I need to do is multiply here. The first one's not a 74. The probability the first one's not 74 is 99 out of 100. The second one's not a 74, 99 out of 100. The third one's not a 74, 99 out of 100. So we just multiply these 3 together. We can think of this as getting 3 failures, sort of like in Bernoulli, where we're talking about success, failure. Success is a 74, failure is not a 74. I have 3 failures here. Let's try probability X is 3. That's something we've done in the past as well. So I'm not going to do X is 1 and X is 2 now. I'm going to go to X is 3. 3 means I have 3 successes. That means I drew a 74 each time. The first one's a 74, the second one's a 74, the third is a 74. We just multiply the 3 probabilities together because they're independent events, okay? These 2 were the easiest. Now let's focus on probability X is 1. What does probability X is 1 mean? It means that out of my 3 draws, I got 174. How many different ways can that happen? Now, this doesn't say, which is stuff we've done in the past, it doesn't say the first one's a 74, and then the second one is not, and the third one is not. All it's saying is that one of them is a 74. It could be in the first spot, it could be in the second spot, or it could be in the third spot. So there's 3 situations that could occur. The first draw could be a 74, the second one is not a 74, and the third one's not 74. So the probability of that happening was 1 out of 100 for that first spot. And then we have two x's, not 74. Those are 99 over 100. Or what could happen is the first one's not a 74, the second one is, and the third is not. I'm thinking sort of like those x's and checks. So I have two failures on the end and one success in the middle. And then the third situation that could happen is that my first two numbers are not 74 and the third one is. Okay? So notice that all of these probabilities are the same. They're all 99 over 100 twice times 1 over 100. Okay? And in mathematics, it doesn't matter how we multiply, like the order, we always get the same number. So if we multiply these three things together, in the first example here, excuse me, if we multiply the first three things together, we're going to get 99 over 100 squared times 1 over 100. That's going to be the same thing as the second one and the same thing as the third one. So really, the probabilities are all the same for each one of these scenarios. We just have to figure out how many different ways we can move that 74 around. There's three ways here. Or it's like thinking of three spots and we're choosing one of them for a check. So we can write the probability of x is 1 is 3 times 1 over 100 times 99 over 100 twice, okay? And that 3 in the front is actually 3 choose 1. We just simplified it to 3. Let's try the second one. Probability x is 2. So think about it. That means we have two 74s and one number that's not a 74. Okay, so the first one could be a 74, the second one could be a 74, and the third is not. Or the first one could be a 74, the second one is not, and the third one is. Or the first one's not a 74, the second one is, the third one is. So what I'm asking here is how many different ways can I move two checks around in three spots? There's three ways. And for each one of these ways, the probability of it happening, I have two failures, which is, I have two successes, which is 1 out of 100, and one failure, which is 99 out of 100. So we have found all of the different probabilities. And the probability x is 1, that 3 can also be written as 3 choose 1. And this 3 in the second probability x is equal to 2 can be written as 3 choose 2. I'm going to do one more, and then we're going to learn how to plug this into the calculator. So suppose you randomly draw 6 cards out of a deck with replacement. Let y represent the number of jacks you draw. Okay, what is the range of y? So y, if I'm drawing 6 cards out of a deck with replacement, I could get no jacks. I could get 1, 2, 3, all the way to 6 jacks. Don't forget the 0. That's a possibility. You could have no jacks whatsoever. So the probability y is equal to 0. That means I have no jacks. When I draw my 6 cards, all of them are not jacks. The probability that the first one's not a jack is 48 out of 52. The probability the second one is not a jack is 48 out of 52. I'm going to have 6 spots with all x's, all of them not being a success. So the probability is 48 out of 52, and I'd have it 6 times. So that's what I've written here, 48 out of 52 raised to the power 6, meaning I have it repeated 6 times. I want to find the probability y is equal to 1, but before I do that, let's see if we can actually get a decimal approximation for the probability y is equal to 0. So you can put this in your calculator. If you have a scientific calculator, you're just going to put in parentheses 48 out of 52 and raise it to the power 6. Or you could put 48 out of 52 times 48 out of 52 times 48 out of 52 6 times, and you should get about 0.62. Let's see if we can put it into Google Sheets or Microsoft Excel. So I'm going to go back to my spreadsheet, and just somewhere randomly, I'm going to type equals, and in parentheses, I'm going to say 48 out of 52 and I'm going to raise that, so that's shift 6 to the 6th power because I have 6 cards I'm drawing, and I get 0.618, which is about 0.62. I was just checking to see if it was the same as what I had on the PowerPoint. And so you can see if I round this to the 100th, it's 0.62. If you're working with a calculator, make sure that you can get 0.62 in your calculator. Okay, let's go back to the probability y is equal to 1. That means I have 6 cards I'm drawing out, and only one of them is a success. So let's think about all the different ways we can move that around. We have one success. So it could be in the first spot, it could be in the second spot, the third spot, fourth spot, fifth spot, or sixth spot. That's success. But the other 5 are going to be failures. So I'm going to have one success, which is 4 out of 52, and 5 failures. And the number in the front is the number of different ways I can move a check around in 6 spots. So, for example, here's 6 spots. The first one could be the success, drawing a jack. Or I could put it in the second spot. There's 6 different ways to move that check around. So this is 6 spots, choosing one for a check. So our answer is equal to 6. We could write it either way. So we could write it as 6, 4 over 52 to the 1, 48 over 52 to the 5th, or write it like this. They're equal to the same thing. Let's try to put that into the calculator to get a decimal approximation. Now, this is called the binomial distribution. And I'm going to show you 2 ways to do it. I'm going to actually enter it exactly the way it is, and then I'm also going to put it as a binomial distribution, like a code. The first thing I'm going to do is I'm going to find 6, choose 1. So I'm going to type equals combination, C-O-M-B-I-N, parentheses, 6, comma, 1, 6, choose 1, and that's 6. Then right beside it, I'm going to enter equals, I want to do 6 times, well, the probability of success was 4 out of 52, so I'm putting that in parentheses. Make sure you put the times symbol. Then I'm going to do times, and we had 48 out of 52 raised to the 5th because there were 5 failures and 1 success. And then I'm going to hit enter. And so the probability of choosing 1 jack out of 6 cards with replacement is 0.309, or about 0.31. Now that was a little tedious. I had a lot of things I had to enter. So we can use this formula that I have written here to find the same thing. So this distribution shows up a lot in mathematics, and they have a formula for it already programmed into Google Sheets or Microsoft Excel, whatever you're using. So how we can get the same number without having to enter all of the things in parentheses is we can over off to the side, we're going to hit equals BINOM, that's for binomial, dot DIST. And then you can already see it's telling you binomial distribution. You're going to put a parentheses right there. And you're going to say, how many successes do you want? So remember, there were 6 spots, and only one of them was a success, comma, how many spots were there? There were 6, comma, what's the probability of you succeeding, of you getting a jack? Well, that was 4 out of 52, comma, and then it's asking you something about cumulative. We're going to put false here. Cumulative means, do you want everything under 1 as well? Like all of the different situations that could occur under 1. But right now, it doesn't make sense, but we're just going to put false all the time, okay? And then let's see what happens. So I get 0.309, exactly what I got here. So depending on what you want to do, you could put it like, if you're putting it in a calculator without Google Sheets or Microsoft Excel, you should get 0.31 if you put it in properly. But with Microsoft Excel, you can find it as well by just using this formula. Let's go back. Here we are. So this probability, if we simplify it, is 0.31. Now on homework or a test, I would want you to find the decimal approximation and not just this formula. Okay, let's see if we can figure out the structure for probability y is equal to 2. So that means we have 6 cards. We draw 2 that are jacks and 4 that are not jacks. So we should have 2 successes, so 4 out of 52 twice, and we should have 4 failures, so 48 out of 52 4 times. So we already have most of the formula here, and now we need to figure out what goes in front. So we have 6 cards, and we want 2 successes, so that's going to be 6 choose 2. And here I'm just showing you like 3 of the different options for choosing 2 successes out of 6 spots, but 6 choose 2 is 15. And so that is what's going to go in the front, 15, or you could just put 6 choose 2. Now let's check to see what that actual probability is as a decimal. So I'm going to go back to the Google Sheet. Okay, and down here, just somewhere over here, I'm going to put the combination formula, which was equals combination 6 comma 2, and I get 15. And then if I want to do it by hand without using the binomial formula here, what I'm going to put is equals 6 choose 2, which was 15, times, we wanted 4 out of 52. We wanted 2 of these successes, times we want 48 out of 52. We need 4 of those because those are failures. And if we hit enter, we get 0.0644. So the probability that we draw 6 cards and exactly 2 of them are jacks is 0.06. There's about a 6% chance that that would happen. Now we can use the binomial distribution formula. It's equals BINOM dot DIST, parentheses. The number of successes we want is 2. We have 6 trials. The probability of success we said was 4 out of 52. And we're always going to put false here. And we get 0.0644. So again, you could choose either way to do this, but this one is probably easier because there's less work with this formula. So now that we see how to do it for 0, 1, and 2, can we come up with a formula? So for any y we have, whether y is 3, 4, 5, or 6, can we come up with a formula that describes the probability? So the formula is however many successes we want, that's the number of checks, we're always going to have 6 choose whatever that number is. So let's say it's k. It's going to be 6 choose k. If k is 3, for example, if k is 3, then it would be 4 over 52 to the 3rd power. And then the 48 out of 52, you take the number of spots and you subtract the number of successes. So in general, a random variable has a binomial distribution if the range is 0, 1, 2, 3, all the way to however many trials you have, and x counts the number of successes. There is a success probability p. In our last example, it was 4 out of 52, but this is more generalized. And the probability that you get a certain number of successes, what you do is you say, let's say there were 10 trials or 10 cards you're pulling out. You put 10, choose however many successes you want, the probability of success raised to that power, and then the 1 minus p, so that 48 out of 52, the failure probability raised to the number of trials minus the number of successes. And this is the formula you would use in Excel to get the answer to any problem involving the binomial distribution.